thank the organizer for giving me the chance. So I am Dr. Saravanan from St. Joseph University. So I will be talking about the non-equilibrium driving protocol for generating entanglement in classical Brownian particle. So when we talk about entanglement, we always think of quantum mechanics, but can we have an entanglement like correlation in classical Brownian particle? The answer is yes. So we will discuss. The mathematical definition for quantum entanglement is if the giant density matrix for a two-particle bipartite quantum system, if we can write in terms of the probabilistic linear mixture of marginal density function density matrix, then these two particles are separable, meaning they are not entangled. If we can't express in this way, then the particles are entangled. Similarly, we can define the same for a classical Brownian particle. When we have a joint distribution function for a two Brownian particle, if we can express in terms of the marginal product of the marginal distribution function, the mixture over the hidden variable, then the Brownian particles are not entangled. If we can't express in this way, then we can say the two particles are entangled. So this is the classical analog of uncertainty product. It's a function of temperature. If we minimize the sum, we can express this variance in terms of sum as a simpler to make it as a simpler expression. We can do this conversion. So this for one particle. If we express for two particle, then this on the right hand side, instead of 2t, it will be 4t. So again, this left hand side, this expression, we can write it for a coupled variable in this way. So we can have A is the summation of all the variants of x and velocity. Here use velocity, which is osmotic velocity, which comes from the slope of probability distribution function. For a separable state, this cross correlation term will always be a positive number, and any of this A are all variance. This can't be negative. Again, this is a positive quantity. For a separable state, the left hand side will always be greater than 4t. If the system is non-separable, meaning that if they are entangled, this will be less than 4t. So whenever a system is entangled, we call the entanglement witness function, that is the left hand side of this equation, will be less than 1. Otherwise, less than 40. Otherwise, it will be more than 40. T is the temperature. So this is the system that we consider. We consider two Brownian particles that are coupled with two independent thermal reservoirs, and they are coupling by a energy term G times x1 and x2. So this is the lambda 1 is the time dependent stiffness coefficient of first particle. Lambda 2 is the time dependent stiffness coefficient of second particle. And if G is greater than 0, then it's a repulsive coupling. If G is less than 0, it's an attractive coupling. This is the potential landscape of both particles. So we can express this to coupled Brownian particle in terms of the two coupled Langevin equation, overdamped Langevin equation. Here symbol have the usual meaning, and the noise is the delta correlated white noise. Expressing this to coupled equation in terms of the matrix equation, we can write the position as the column matrix of this. Similarly, noise can be written in this way, and this is the matrix coupled two different Langevin equation. So since the system is linear and noise is Gaussian, so it's dynamics will be completely determined by the covariance matrix, and the time evolution of this covariant matrix can be determined by deterministic Lyapunov equation, and this is the diffusion matrix. This is the protocol that we followed. Since these two particles are confined by a time-dependent stiffness coefficient, we can vary the stiffness coefficient from initial value lambda naught to final value lambda naught. So here E stands for expansion. Expansion means initially the particle is at 2 lambda naught, and when we drive for a time of tau, finally it will come to the lambda is equal to lambda naught. So lambda is decreasing here. Initially it is 2 lambda, finally it is lambda. It's like a trap is expanding. That's why I designated this as E. The same is for second particle also. And then stringing means initially the particle is in lambda naught, final stiffness coefficient is 2 lambda naught. So I denoted it by S. So this is symmetric. Both particles is being expanded, both particle is being shrunk, and again one particle is shrunk, another particle is being expanded. Here first particle is expanded and second particle is shrunk. So these are the 4 different driving protocol that we use to drive the system from equilibrium to out of equilibrium, to bring it to the out of equilibrium state. So this is the non-Gaussian parameter, kurtosis -3. So we can see over the duration of driving, both particle 1 and particle 2 in the EE case, when both particle trap stiffness is expanded, they maintain the Gaussianity. Again, for all 4 cases, the system is in Gaussian state only. Here you can see the entanglement witness function that I showed you earlier. Initially, there is one red color line. This is 40 line. You can see 40 line is here. For here, we drive the system for a tau is equal to 0 to 4 second. 0 to 4 second. For some particular time, the system comes to entangled state, again going to non-entangled state. This is for E case, when both particle trap is being expanded. When one is expanded, another is shrunk, it again maintain the entangled state for some time. The same is here also, and then for both stringing case also, it maintains entangled state for some time. And this is with respect to G, here x-axis is G. When I have 0 G, you can see all the particle initially they are in non-entangled state, but when I increase G till 4, you can see for first case, the particle always will be in the entangled state for all the values of G, and for in the second case, till certain G, it maintains the entangled state, again it jumps. The same is here also. Here also you can see. So these are some conclusions. So the main observation we driving causes the system from non-entangled state to entangled state, and then it's depend on the initial state and the variance of the fluctuations of the difference in position and fluctuation of the velocity. It depends. So these are some of our publications recently that we made. Thank you. Yes.
Hello. Yeah. So this is, you said this is an entanglement witness, right?
Yes.
Is there some entanglement measure in this case, like which can tell us whether something is more entangled than something else?
So that we can find by finding the entropy, von Neumann entropy, but we haven't done that. So we defined a function called entanglement witness, which is only a measure of this function. So it's the variance of the deviations of velocity and position, the difference in position. Means for a separable state, this quantity will be always greater than or equal to 40. If the system is entangled state, this will be less than 40.
But it's not monotonic, right? I mean, like if it is
Yes, yes.
very less than, it's not like it's more entangled or something,
Yes,
right?
yes.
Okay.
So in the plot of kurtosis, why is it, you
kurtosis.
said like X is a Gaussian variable, right?
Is a,
X has a Gaussian distribution.
yes, yes, yes. So
But
it's
why was kurtosis not going to 3 and like before this?
this one.
Yeah, I mean
So
0 or 3 depending on how you define it.
okay, so it's a fourth moment of position divided by second moment squared minus 3.
That should go to 0, like, okay.
It's almost close to 0 for all the case, you can see.
Do we have any more questions?
So you talked about classical entanglement and the hidden variable lambda.
Yes.
So how is this like?
Actually, it depends on how initially we arrange the particle. So we can have one particle in one state, another particle in another state with a probability of P of lambda. P of lambda can vary from 0 to 1. So it depends how we arrange the system initially.
So again, what is the hidden variable like physically?
Physically, it's some parameter. It depends on how we prepare the system initially. Hidden variable, what can I say?
Okay, I think we can thank the speaker.
Okay, thank you.